We're going to start section 5.6 on page 388 about dividing polynomials by binomials. So I'm going to provide you with the steps the way I understand them. So we're going to first we're going to write the fraction or the division by using a division box. So usually you're going to have a fraction with the numerator and a denominator. So we're going to use the division box, and inside of the division box, we're going to write the numerator, and outside we're going to write the denominator. Usually we're going to call this the dividend. This is going to be the divisor, and what we're going to obtain up here is going to be the quotient. So we're going to use the division box that we used to use when we were at the high school or elementary school or middle school. So then we're going to proceed with the process that we learned at that time. We're going to divide the leading term of the dividend by the leading term of the divisor. So we're going to work on the leading terms to get the quotient term. Then we're going to multiply the quotient term and the entire divisor. We're going to write the result with opposite sign below the dividend. And then we're going to combine like terms of those algebraic expressions. So we're going to repeat the process with the new dividend. So we're going to start again with division, multiplication, and subtraction, and then division, multiplication, and subtraction until we don't have more terms too in the dividend. So I'm going to solve some examples, and then you're going to do this. So again, we're going to have a polynomial divided by a binomial. So, and there are two different ways to do this. So we're going to use today something that we call the long division process, where essentially we're going to write the fraction by using the most common notation, using the division box. So we're going to write the polynomial is going to be the dividend, and the binomial is going to be the divisor. So this is the long division. There is another method that is faster than this method. So that method is the synthetic division. Synthetic division. So you're going to learn about this on Math 263 or on Math 13. So if you take those courses, you're going to learn how to divide faster a polynomial by a binomial. So I'm going to start with example 2. So let's write here example 2 on page 399. So the problem says divide, and then they provide a fraction where the numerator is a polynomial with 4 terms, and the denominator is just a binomial. So before writing the fraction by using a division box, we need to arrange both the numerator and the denominator in descending powers of the variable, in this case, in descending powers of x. So that's our step 0. So you're gonna arrange the terms in the numerator and the denominator in descending powers of the variable of interest. So in this case, we're gonna start with the term with the highest power. So in this case, we need to write first 4x cubed. Then we look for the next one. Is going to be negative 4x squared. Then the next one is 7x, and finally negative 9. So now I have the polynomial, which is of degree 3 because that's the highest power. So a polynomial of degree 3 divided by a binomial. So the binomial is written in the right way. So we start with the linear term, then we end with the constant term. In this case, is the cubic term, the quadratic term, the linear term, and the constant term. So we're going to write this division in the other format. So the old format. So we're going to write the dividend. So the dividend is going to be 4x cubed minus 4x squared plus 7x minus 9. That's the dividend. Then I'm going to write the divisor, 2x minus 1. So again, this is the dividend, and this is the divisor. So we're going to repeat the steps many times. So we're going to have some cycles. We're going to start with the first cycle. I'm going to write here on the left all the operations I'm going to perform, and then you're going to see on the right how the division proceeds. So I'm going to start with the first cycle. So the first step is we need to divide the leading term. I'm going to write the leading term of the dividend over the leading term of the divisor. Okay, leading term of the dividend over the leading term of the divisor. So what are those terms? So this is the leading term of the dividend, so it's 4x cubed, and this is the leading term of the divisor, so it's going to be 2x. So I have the division of two monomials. You know how to obtain the result. You divide coefficients, 4 over 2 is going to be 2. You divide variables, x cubed over x is going to be x squared. So that is going to be the first term for the quotient. So this is going to go to the quotient. So I'm going to write 2x cubed, 2x squared here. And then the next step, we're going to multiply this term, 2x squared, by the divisor, the entire divisor. So we copy the entire divisor. So we now apply the distributive property here to do this multiplication. So we're going to have 2 times 2 is going to be 4x cubed, and 2 times negative 1 is going to be negative 2, and then x squared. So this is the result. Now I'm going to write this on the next row. I'm going to write it here, but in the process, I'm going to switch the sign. So you're going to need to switch signs. So 4x cubed is going to become negative 4x cubed. Negative 2x squared is going to become positive 2x squared. And then we're going to combine like terms. So again, our step 3 is just write the product. This is the product with opposite sign. So that's what we did here. Then the next step, we're gonna combine like terms to get a new dividend. So let's do that. So 4x cubed and 4x cubed with opposite sign, these cancel to each other, and that's what we wanted. If you don't cancel the leading term, then something went wrong. So then you have negative 4 and positive 2 is going to be negative 2x squared, and then you bring down the rest of the previous or the initial dividends. So I'm going to write positive 7x, negative 9, and now we have a new dividend, so to speak. So what I'm going to do now is I'm going to repeat again these 4 steps. So I'm going to start a second cycle. I'm going to have a second cycle, and then I'm going to start again with dividing the leading terms of the dividend. The new dividend now is this. So I'm going to write negative 2x squared over the leading term of the divisors. That doesn't change. It's going to be always the same. So I'm going to divide by 2x. So again, I'm going to divide two monomials. So I'm going to get a negative 2 over 2 is going to be negative 1, and x squared over x is going to be just x. So this is another term for the quotient. So I'm going to write negative 1x, which is just x, right? But I'm writing everything in the way that I'm getting. So negative 1x. Now I'm going to multiply this term by the entire divisor. So that's my second step. We multiply negative x and the entire divisor, 2x minus 1. So we're going to get, in this case, we're going to get negative 1 times positive 2 is going to be negative 2x times x is going to be x squared, in negative times negative is going to be positive 1x is just 1x. So that's the second step. The third step is that we're going to write this here with opposite sign. So my third step is just switch signs. So I'm going to write positive 2x squared, and I'm going to write this positive x is going to become negative x. So I'm going to proceed with doing the fourth step is just combining these two. So again, the leading term of the current dividend should cancel, and then we get a new dividend. So this is going to be positive 7x minus x is going to be 6x, and we bring down the remaining part of the previous dividend. So we have another new dividend now. So we're going to repeat this process one more time. So this is going to be the third cycle. So the third cycle is going to be first, the leading term of the new dividend is 6x. 6x divided by the leading term of the divisor is just 2x. So I'm going to divide this by 2x. So again, I'm dividing two monomials. I'm going to get 6 over 2 is going to be 3, and x over x is just 1. They cancel to each other. So this is another term for the quotient. So it's going to be positive because this 3 is positive. I need to write a sign all the time, positive 3. So now I'm going to multiply this positive 3 and the entire divisor. So that's my second step here. 3 times the entire divisor. So what is the answer of this? The answer of this is going to be 3 times 2 is going to be 6x. 3 times negative 1 is negative 3. So we're going to write this here with opposite sign. So I'm going to write negative 6x and negative 3 becomes positive 3. So I'm going to do another addition here. I'm going to combine like terms. So again, leading terms should vanish. So I'm going to get just negative 9 plus 3 is going to be negative 6. So this is the final step. So this is the remainder. So I have now the dividend, the divisor, the quotient here. So this is the quotient. This is the divisor. We have the dividend over here, and now we have the remainder. So once you master these steps on the left, the only thing that you're gonna need to write is this. So, but yeah, I'm explaining every single step on the left part of the page. So now we need to write just the final answer to understand a little bit about terminology of division. So we started with this polynomial 4. So this is gonna be, we're gonna express the final result. So we have 4x cubed minus 4x squared plus 7x minus 9. We divided this by 2x minus 1, and the answer is the quotient. So we're going to copy the quotient from here. We're going to copy this entirely. So 2x squared. So this is going to be 2x squared minus x plus 3. So this is the quotient. This is the quotient. And then we're going to add a fraction. And that fraction is going to contain in the numerator the remainder, which is negative 6. This number here. So we're going to write the remainder, and we're going to write the divisor, 2x minus 1. So this is the final answer. So this is the remainder. So the remainder, this is the actual weight, or the best way to write the remainder is negative 6, and we need to write the divisor. So this is the division, the long division. I'm going to solve one more problem. I'm going to assign you a couple of problems, and we're going to continue with the next section. So we're going to solve one more example, especially because you're going to see what happens when you don't have all the terms in the sequence of powers. So let's say that you have only x cubed, then you have x, and you have negative 9, but you are missing the quadratic term. You need to add something here. You need to write something here to be able to perform the long division. And that's what we're going to do with the next example. So we're going to have now our next example is example 3. Example 3 on page 394. The problem says that we're going to divide ax cubed minus 1 over 2x minus 1. So the first thing is that you see that we have a cubic term, but we are missing quadratic and linear terms. So we need to rewrite this in another way. So that's what we're going to do now. So I'm going to write first the the division box. I'm going to write the first term, ax cubed. Since I don't have a quadratic there, I'm going to write 0 x squared plus 0x because I don't have a linear term. And finally, negative 1. So now I have my dividend. The divisor is similar to the divisor that we used the last time. It's just a coincidence. So that's the divisor. And we're going to start right away with the first cycle. The first cycle. So we're going to divide the leading term of the dividend, ax cubed, over the leading term of the divisor, 2x. So we're going to get a divided by 2. So we divide coefficients first. And x cubed divided by x is going to be x squared. And this goes to the quotient. And now you see the reason of adding zeros here is just to align the like terms. So 4x squared goes in the second column, 4x squared. So otherwise, it's going to be a little, our quotient is going to be a little bit messy. It's not going to correspond with the dividend. But yeah, if you understand what you are doing, you don't need to add these zeros here. But this is better when you want to have your work organized. So now, second step of first cycle is just multiplying the term that we just found by the entire divisor. So this is going to require applying the distributive property. So we're going to apply the distributive property here. So we're going to obtain 4 times 8 is going to be, sorry, 4 times 2 is going to be 8. X squared times x is going to be x cubed. Then positive times negative is going to be negative. 4 times 1 is negative 4. And then only x squared. Then we're going to write this here with opposite sign. So we need switch the sign. So this is like multiplying by negative 1. So this is going to be negative ax cubed and positive 4x squared. Another reason to see why we need 0x squared here. So now we're going to combine like terms. So leading term is going to vanish. And then we're going to end up with only 4x squared. Then we bring down the other terms, 0x, negative 1. So I have a new dividend now. So I'm going to start the second cycle. The second cycle is, again, we're going to divide the leading term of the new dividend for x squared by the leading term of the divisor. So that gives us 4 divided by 2 is going to be 2. X squared divided by x is just x. So that term goes to the quotient. Again, we need to add a sign, positive 2x, because if you only write 2x, the expression is going to be confusing. So we need signs in between terms. So then we're going to multiply 2x and the entire divisor. So we're going to need to apply again the distributive property. So we're going to multiply these 2 and these 2. So 2x times 2x is going to be 4x squared. Negative 1 times 2x is going to be negative 2x. So I'm going to write this over here with opposite signs. So it's going to be negative 4x squared positive 2x, because negative times negative is going to be positive. We're going to switch signs. So now we combine like terms. So we're going to cancel these 2. I'm going to end up with 2x minus 1. So this new dividend is going to be divided by the divisor in my third cycle. So I'm going to have now leading term is 2x. Leading term of the dividend, leading term of the divisor is 2x2. So this is just 1. And this one goes to the quotient. We need to write a sign. The sign is positive. So that's 1. Then the second step is just multiplying that 1 and the entire divisor. So one more time, we are applying the distributive property. So we're gonna get 2x plus 1. Now we're gonna write this here, but with opposite sign. So it's gonna be negative 2x, positive 1. And you're gonna see that you can cancel this and this and this and this. So you end up with a 0 remainder. So we're gonna write the final answer here. So the final answer, the final result can be written as, if you have ax cubed minus 1 over 2x minus 1, that's the original problem. You can write this by writing the quotient 4x squared plus 2x plus 1, that's the quotient. And there is no remainder because it's 0. So you don't need to write the fraction that goes here. So this is plus 0 over 2x minus 1, but 0 over 2x minus 1 is just 0. So there is no need to write it. So you're going to solve a couple of problems from 5.6, exercise set on page 395. So you're going to solve problem 20. It's just 9y plus 18 minus 11y squared plus 12y cubed. You're going to divide this polynomial by 4y plus 3. Then we have one more. That's problem 28. So we have 4y cubed plus 3y plus 5 over 2y minus 3. So this is your first assignment for this lecture. So you're going to take maybe 15 minutes to work on these two divisions, the polynomials by binomials, and then we're going to continue with the next section. We're almost finishing chapter 5. This is section 5.7. That's the last section of this chapter. It's about negative exponents and scientific notation. It's on page 398. So there are two main components of this section. First, we're going to start talking about negative exponents, and then at the end, we're going to work on scientific notation. So the first thing is we're going to learn about two rules that we're going to need to work when we have negative exponents. The first thing is that you need to remember that we don't like negative exponents. So we have these rules to get rid of negative exponents. So the only purpose of these rules is to rewrite an expression that contains negative exponents into another expression. We're going to convert that expression into another expression that doesn't contain negative exponents. So we only want positive exponents everywhere in the algebraic expression. So the first rule is the negative exponent rule, which is on page 399. So anytime that you have a negative exponent in the numerator, you can move that part of the expression to the denominator, and by doing that, now you switch the sign. So if you have any expression, any variable with a negative exponent, and that variable is in the numerator. So you don't see here that this is a fraction, but you know that you can write this as b to the negative 1 over 1. Then you're going to move that to the denominator, and by doing that, we can switch the sign of the exponent. And in this case, you need to take into account that this b to the negative 1 is multiplying a number 1 that we don't see. So that's the reason that we are left with a number 1 in the numerator. So the most common mistake that the students make when they are working with negative exponents is that when they move the quantity with a negative exponent to the denominator, they put 0 here because they think that there is nothing after this quantity moves to the denominator, but there is something, it's a number 1. Here is, you can see easily what happens when you have the variable with the negative exponent in the denominator. Then you move it to the numerator, and then you switch the sign. See, this is just a game of moving variables from the numerator to the denominator, or from the denominator to the numerator, to switch the sign of their exponents. So let's work some examples. So I'm going to work example 1 on page 399. So we just need to rewrite, as I mentioned. We don't like negative exponents. So in this example, we're going to rewrite the expression. We're going to rewrite each expression with a positive exponent. With a positive exponent. So we don't like negative exponents. So we're going to start with 7 to the negative 2. So the thing that we're going to do is we're going to write 7 to the negative 2 over 1 to see the process. And then we're going to move this expression, this quantity with a negative exponent, to the denominator to switch the sign of this exponent. So if we do that, we're going to end up with 7 squared. But again, this quantity is multiplying 1, so we end up with 1 here. Then we finish just simplifying the indicated operation, because we know that 7 squared is just 7 times 7. So the final answer is 1 over 49. So that's another reason to switch negative exponents to positive exponents, because in that way we are able to do some operations. Otherwise, it's very hard to understand how we're going to find the result of 7 raised to the negative second power. So let's work on the next problem. We have 4 to the negative 3. So again, we need to see that this 4 to the negative 3 is in the numerator of a fraction. Then we're going to move it to the denominator to switch its sign, the sign of the exponent. So now it's going to be 4 to the cube. And then we finish by rewriting the exponential expression as a multiplication. So remember, this is the base. The base multiplies itself 3 times because 3 is the exponent. And finally, we just use a calculator to find the final answer. Okay, one more problem. We have negative 2 to the negative 4. So it looks like a very complicated thing. So first we need to understand that this is the base. So we can move this base to the denominator. And at the same time, we're going to be able to change the sign of the exponent, not the sign of the base. I'm going to change the sign of the exponent. So now the exponent is positive. The base is still negative, it's a negative base. That's the reason we are using parentheses to indicate that the base is negative. Now the final step is just multiplying the base by itself, in this case 4 times. So this is going to be negative times negative times negative 4 times. You're going to get positive 1/16. So that's example 1. I'm going to write now another example. So now we have example 2 on page 400. So again, we need to write the expressions with no negative exponents. So we're going to start with the first one. The first is just 4 to the negative 3 over 5 to the negative 2. So in both cases, we have negative exponents both in the numerator and the denominator. So we're going to just flip these two. We're going to swap. So we're going to end up with 5 now in the numerator, but with a positive exponent. And we're going to end up with 4 in the denominator, but now with a positive exponent. So then the final step is we need to rewrite every exponential expression as a multiplication. So it's very important that you remember all this kind of work. So the final answer is just 25/64. And then you check whether you can still simplify more the fraction. So now we have part B is 3/4 to the negative 2. So first we're going to apply a rule that allows us to break this base into parts. So one is going to be the numerator with the exponent and the denominator with the same exponent. I've just broke the base, which is a fraction, in 2 parts. Now I'm going to apply the rule of negative exponents. So that means I'm going to write this 4 on top with a positive exponent and this 3 on the bottom with a positive exponent too. Then I'm just going to rewrite the exponential expression as a multiplication. So this is going to be just 16/9. So that's example 2, parts A and B. There are 2 more parts of this example, so let's work on those. So I have part C is 1/4x to the negative 3. So we find the base that has a negative exponent. So the base here is just x. That base is the one that has this negative exponent. So that's the only part that is going to go up. The other part is going to remain here. So we're going to have x to the cube on the top. That base was moved to change the sign of its exponent, but the other part remains because the other part doesn't have any negative exponent. So that's the answer. Finally, we have x to the negative 5 over y to the negative 1. So we're going to do the same thing as before. We're going to swap the numerator and the denominator. So we're going to get y to the 1 over x to the 5th power. So this is just y over x to the 5th power. So now, before solving the next example, I'm going to show you that there is a table. There is a green box on page 401 that summarizes all the rules of exponents that we have been using so far. So it's good if you take a screenshot of this green box. Contains the product rules, the power rules, and now the negative exponent rules. So we need this information to be able to solve any problem involving exponent. So you can see here now the table or the green box I'm talking about. So you have the rules on the left part, and you have an example to remember how to use that rule. So now we're going to use all the rules that we have learned so far to simplify some algebraic expressions. So let's do that now. So I'm going to work on example 3. So let's see. We need to write here example 3. So study and memorize the rule for exponents. All the rules that are here in that green box. So we're going to start with example 3 to apply all those rules. This is on page 401, and this is about simplifying. So we need these rules every time because we need to simplify algebraic expressions all the time. So we have on example 3 just x to the negative 9 times x to the 4. So now we have the product of two expressions with the same base, but now we have negative exponents involved. So first we're going to apply the rules that have to do with the product of this variable. So you know that the base is x, and then you're going to add or you're going to combine the exponents. So you have negative 9 plus 4. So negative 9 plus 4 is going to be x to the negative 5. Then we don't like negative exponents, so we need to move this x to the negative 5 to the denominator. So we're going to get x to the 5th, and we leave a 1 here. So that's the final answer for example 3. Then we have example 4, page 401. So this is about more simplifying. So well, now we have 3 cases. We're going to start with x to the 4 over x to the 20th. So we know the rule when we have a fraction or quotient. So we're going to write x to the 4 minus 20. So we subtract the exponent in the denominator from the exponent in the numerator. Then we write the answer is going to be x to the negative 16. We have a negative exponent. We don't like that. So we're going to need to move that part of the expression to the denominator to be able to get it with a positive exponent. So that's the final answer. So we have another example now. This is 25 x to the 6 over 5x to the 8. So we divide coefficients and we get the quotient of variables. So in this case the base is x, exponent from the numerator minus exponent from the denominator. So we get now 5 x to the negative 2. We don't like negative exponents, so we're going to move this x to the negative 2 to the denominator to get it with the positive exponent. And we leave 5 on the top because 5 doesn't have any negative exponent. So that's the answer. Then the last case is just 10 y to the 7 over negative 2 y to the 10. So we're going to divide coefficients, 10 over negative 2, and we're going to divide variables by subtracting exponents, in this case exponent from the numerator minus exponent from the denominator. So we're going to have positive divided by negative is going to be negative, 10 over 2 is going to be 5, and y is going to be to the 7 minus 10 is negative 3. So we need a 1 here to move this y to the denominator and get it with a positive exponent. So that's example 4. Now we have example 5. Example 5 on page 402. So we're going to simplify. We're going to simplify 5x cubed squared over x to the 10. So we're going to distribute the exponent over these factors inside of the parentheses. So you're going to have 5 squared, x to the 3 times 2 is going to be 6 over x to the 10. So this is going to be 5 squared is just 25, and then we divide the variable x. So it's going to be 6 minus 10. So this is 25x to the negative 4. So we need to move this x to the negative 4 to the denominator. So we're going to end up with 25 over x to the 4. Okay, that's example 5. Then you're going to need now to work some exercises in the exercise set. And then we're going to start with scientific notation. So we have 5.7 exercise set on page 408, and you're going to work these 3 problems. So you're going to work problem 38. You're going to simplify 45z to the 4 over 15z to the 12. Then we have problem 58. You have just 4x to the negative 1, and that is raised to the negative 2. And finally, problem 78 is going to be x cubed over y squared, and this is raised to the negative 4 power. And I need you to work on those 3 problems. So I'm going to give you time, 10 minutes or so, and then we're going to continue with the last part of this section, which is scientific notation. So the final part of this chapter is about scientific notation. It starts on page 403. And scientific notation is the way scientists express very, very large numbers or very, very, very small numbers. So the way that we're going to express those huge numbers or very, very tiny numbers is by using this expression here. So we're going to have a number. This is going to be a number, then times, the symbol for times, 10, and then an exponent. So we're going to use powers of 10. So this is a power of 10, and the power of 10 are going to be multiplied by a number. This number is going to be known as a mantissa. The mantissa is a number whose whole part, So the whole part is between 1 and 9 inclusive. So meaning that you can have 1 point something, 2 point something, up to 9 point something. Those are Mantissas. If you have 13 point something, that doesn't qualify for a Mantissa. If you have 0 point something, that doesn't qualify for a Mantissa either. So you need 1 point something, 2 point, 3.4, up to 9 point something, and that's it. Other possible whole parts don't qualify to be a mantissa for scientific notation. So we're gonna need to be able to convert numbers from one notation to the other. So we know we call the notation that we use most of the time as decimal notation. So when you write 300, it's just decimal notation, but you can write 300 by using scientific notation. So and we're gonna learn how to do that. So we're gonna start converting numbers from scientific notation to decimal notation. So to do that, we're gonna have two rules to move the decimal point of the mantissa. So that's the way that we're gonna move from one notation to the other, by playing with the decimal point of the mantissa. So you have only two options. You either move the point to the right or you move the point to the left. So these are our two main rules to deal or to work with the conversion of numbers from one notation to the other. If you move the point, the decimal point to the right, you need to subtract the number of places that you move the point from the exponent of the power of 10. So anytime that you move the point in the mantissa, you're gonna need to modify the exponent of the power of 10. If you move the point, the decimal point to the left, then you're gonna need to add the number of places that you move the point to the exponent of the power of 10. So anytime that you move to the left, you add a value. Anytime that you move to the right, you subtract a value. When you convert numbers from the decimal notation to the scientific notation, you're gonna start writing the number as a power of 10. Any number in decimal notation can be written as the number times 10 to the 0, because 10 to the 0 is 1. We know that any number raised to the power 0 is 1. So any number multiplied by 1 is just the number, is the same number. So this is the trick that we're going to use to convert a number from a decimal notation to scientific notation. We're going to start by writing the number, then times 10 to the 0, and then we're going to play with the decimal point of the number. We're going to move the decimal point. We're going to move the decimal point to a location that gives us a mantissa, that gives us a number that qualifies to be a mantissa, and then you just count the number of places that you move the point and you adjust the exponent of the power of 10. How? By following the same rules. So we're going to follow these two rules to adjust the exponent, to adjust the exponent of the power of 10. So I'm going to show you how to apply these rules. This is the way I understood the process since I was a student at college. So I'm just giving you the way that I did it. And it worked for me all the time because you don't need to memorize a lot of things. So let me start with solving some examples. And then we're going to do some math involving numbers written in scientific notation. So I'm going to work the first example from this section. So is just example 7 on page, let's see, 403. So we're gonna write each number. We're gonna write each number in decimal notation. In decimal notation. So we're gonna start with 2.6 times 10 to the 7. So any number in scientific notation with a positive exponent in the power of 10 is a number that is bigger than 1. Any number with a negative exponent in the power of 10 is going to be a number that is smaller than 1. So let's start. So this is a number written in by using scientific notation. So this is scientific notation, and we want to find the number in decimal notation. That's the purpose of this. So let's check this number. This number, this is the Mantissa. This is the Mantissa, and this is the power of 10. This is the power of 10. The Mantissa, as you can see, has a whole part and a decimal part. The whole part is number 2, so this is this number 2.6 qualifies as a Mantissa because it's following the rules. It's satisfying the rule that this whole part should be any number between 1 and 9, including 1 and including 9. So it's 2. It's perfect. That's a Mantissa. So now what we're gonna do to find the decimal notation is that we need to move this point either to the right or either to the right or the left, and then anytime that you move the point, the decimal point, you're gonna change the exponent of the power. So the aim of the game is we need to get 10 to the 0 here, because 10 to the 0 is going to be the way that we're going to know that we found the number in decimal notation. So we need a number here, 10 to the 0. So that's the way that we're going to find our number in decimal notation. So we have 2.6 times 10 to the 7. So we're going to need to move the decimal point 7 places. If you move it to the right, you're going to subtract. If you move it to the left, you're going to add. Then you need to move to the right because you need to subtract. You need to decrease this value. So I'm going to write 2.6 here, and then I'm going to add a lot of zeros, and then I'm going to start moving. If I move the point 7 places, 1, 2, 3, 4, 5, 6. So I'm moving 7 places to the right. So I'm moving the decimal point 7 places to the right. That is going to have an effect on the exponent of the power of 10. If I move 7 places to the right, I need to subtract 7. That's the rule that we learned, that we wrote on the previous page. So that means that the final location of this point is going to be here, and because of that, we're going to be able to do this operation. So we're going to get 2, then I have 600, and then 1,000, and then the point is going to end up here, and you can have 1 0 here or more, or not zeros at all. This is going to be times 10 to the 0, but times 10 to the 0 is just 1, so the final answer is this. So that's the number in decimal notation that corresponds to this number in scientific notation. So the game is just moving the decimal point. If you move it to the right, you subtract. You move it to the left, you add. So let's see the second part of this example. So now we have 1.1 times 10 to the negative 4. So this is scientific notation. So now I need to move this decimal point either to the left or to the right. If I move it to the right, I'm going to subtract, so I'm going to get more negative. I need to move it to the left now to add. So I'm going to write my Mantissa, but I'm going to write now zeros on the left because I need to move this point to the left to be able to add here. So I'm going to move this point 4 places to the left. 1, 2, 3, 4 places to the left. I'm going to move the point. I'm going to move the point 4 places to the left. And by doing that, when you move to the left, you add the number of places that you moved your decimal point. You add that number to the exponent of the power of 10. So I'm going to end up with 0 point, and I have 3 zeros, and then 1 and 1. There is no decimal point now between these two ones anymore. So, and that's the answer, because this is going to be times 10 to the 0 again, because negative 4 plus 4 is going to be 0. It's going to be 0. Then 10 to the 0 is going to be 1. So the final answer is 0.00011 is the number in decimal notation. So this is when you need to move your point to the left. Remember, you're going to add. So you move it to the right, you subtract. So you can see here what is the thing that happened. If you move it to the left, you're going to add the number of places that you move the decimal point. So let's work more problems, and then you're going to be able to work on some exercises. So this is example 8 now. Example 8, that's on page 404. Now we're going to write each number in scientific notation. So we're going to work now, we're going to do the opposite procedure or operation that we did before. So we're going to start with 4,600,000. So this is now a number in decimal notation. Now we need to find the scientific notation. So we're going to write this number as a power of 10. So we're going to write 4,600,000. The decimal point is over here. So when you don't see a decimal point, usually it should be at the end of the number, times 10 to the 0. So that's the number that is still in decimal notation, but is written as a power of 10 now. So now I'm going to move the decimal point to a location that is going to give me a Mantissa. So I'm going to write here the number with the decimal point. So if I move the point to this location, I'm not going to get a Mantissa that is going to be between 1 and 9. I'm going to get a Mantissa that is going to be 4,600. This location doesn't work. If I move the point to this location, I'm going to get 46 point something. 46 point doesn't qualify as a possible Mantissa. So you're going to learn how to, it's very easy to identify the location for the decimal point to get a Mantissa. So if I put the point here, 4.6, that qualifies as a Mantissa. If I move the point to this location, I'm going to get 0.4. That doesn't qualify as a Mantissa. So the important part when you are converting a number into scientific notation, into a number in scientific notation, is that you need to find the exact location, the right location for your decimal point. Once you do that, the rest is going to be very simple. So in this case, I need to move the decimal point. I need to move it 1, 2, 3, 4, 5, 6 places to the left. 6 places to the left. So if I do that, I'm going to need, so I'm going to show where the point is going to end up. So I'm going to need to adjust. I have 0 here. I'm moving 6 places to the left. When you move to the left, remember the rule is you add the number of places when you move to the left. So it's going to be plus 6. So what is the final answer? So the final answer is just 4.6, because now the point is over here, times 10 to the 6. That is going to be the scientific notation now. This is a number in scientific notation. So that's the first part of example A. So now let's work the second part of this example. So we're going to have part B. Now we're going to write 0.000023, which is in decimal notation. We need to write it into scientific notation. So we have to write this as a power of 10. 10 is at the 0 power, because I haven't moved the point yet. So I'm going to move the decimal point to this location here, because in that way I'm going to get a Mantissa that is going to be 2.3. So 2.3 qualifies as a Mantissa. So I'm going to move the decimal point 1, 2, 3, 4, 5 places to the right. So if I move the point 5 places to the right, I'm going to subtract 5. That's the rule. If you move to the right, you subtract. If you move to the left, you add. So what is the final number? It's going to be 2.3, because now the point is going to be between 2 and 3, times 10 to the negative 5. So that's the number written in scientific notation. So now you're going to work a couple of examples. So from 5.7 exercise set on page 408. So now you're going to work problem 88. You're going to write 3.14 times 10 to the negative 2 in decimal notation. Then you're going to write, you're going to work 98. You're going to write 9832 in scientific notation. And you can work more exercises from that set. So you need to practice a lot. So it's up to you to work on more. So take some time to work on those problems. And then we're going to finish the section with some math involving operations with numbers in scientific notation. So on page 405, you can see another green box showing the main computations that we're going to do with numbers in scientific notation. So we have the operation of multiplication. So we have a number in scientific notation, a times 10 to the n. Then we have another number, which is b times 10 to the m. So when you multiply two numbers in scientific notation, what you need to do, you multiply the mantissas, and you work on the powers of 10 by adding the exponents. So you add the exponents of the powers of 10, and you multiply the mantissas. So when you are going to divide two numbers that are written in scientific notation, then you're going to divide the mantissas. You're going to divide the mantissas, and you're going to subtract exponents of the powers of 10. So you're going to subtract the exponent from the denominator from the exponent in the numerator. So it's going to be 10 to the exponent in the numerator minus the exponent in the denominator. This is when you subtract, this is when you divide two numbers in scientific notation. Finally, you can raise a scientific number, a number written in scientific notation, to a power. So if you raise a times 10 to a times 10 to the n to the power m, you're going to raise a to the m, so you need to fix the typo here. It should be a to the m, because m is the exponent that you are distributing. A to the m times 10 to the n times m, so this is correct. But this should be a to the m. So you raise the mantissa to the power, a to the m, and you raise the power of 10 to another power by multiplying the exponent. So I'm going to solve one more example or two. One more example only, 3 cases, and then you're going to be ready for the final part of this section. So let's work on example 9. I'm going to write the operations. I think it's better if we have that in our notes. I'm going to write operations with numbers written in scientific notation, because I want to fix the typo. If I only give you the recommendations of look at that table or the green box on page 405, you might forget that we need to fix a typo. So let's write multiplication is just a times 10 to the n times, they use times, you can use just parentheses. I'm going to write this in another way, slightly different from the book. B times 10 to the n, because we know that we can just multiply two numbers by using parentheses. And this is going to be a times b, so we multiply mantissas and then times 10 to the n plus m. So that's the formula, so to speak, for multiplication. For division, we're gonna get, for example, a times 10 to the n over b times 10 to the m. In this case, we're gonna divide mantissas, so a over b times 10 to the n minus m. And finally, exponentiation, so raising a number in scientific notation to a power. So for example, a times 10 to the n raised to the power m. This is going to be equal to raising the mantissa to the power m. That's it. That was the typo. The book has n. That's a mistake. times 10 to the n times m. And all the results should be written in scientific notation. Because sometimes when you multiply Mantissa, you're going to get a number that is going to be greater than 9. Then you need to fix the problem, adjusting the final exponent. When you divide, sometimes you're going to get numbers that are less than 1, Mantissa that are less than 1. You need to move the decimal point to get the right Mantissa. So that's those are the notes that are on the green box on page 409. So now we're going to work examples. One example only, example 9 on page 405. So we're going to compute. The first case is just 4 times 10 to the 5th power that multiplies 2 times 10 to the 9. So that's the first problem. So we said we need to multiply Mantissa, so 4 times 2, then times 10, and we add exponents. So this is going to be a times 10 to the 14. So that's the first problem. The next one, now we have a division. We have 1.2 times 10 to the 6 over 4.8 times to the 10 of negative 3. So this problem is very interesting. So pay attention. We're going to divide Mantissa's 1.2 over 4.8. Then we're going to get the power of 10. So we're going to have the exponent from the numerator minus the exponent in the denominator. So check that the denominator has, the power of 10 has a negative exponent, and we need to get first the negative corresponding to the operation. And then you just simplify this. So 1.2 over 4.8, if you use your calculator, you're going to get 0.25 times 10 to the 6 plus 3 is going to be 9. But now, this is not a Mantissa, because you have 0 here. We need to move the point, the decimal point, to this location. We're going to move it to the right one place. So when you move the point to the right, so I'm going to move the point to this location, 1 unit to the right, or one place. I'm going to move the decimal point 1 unit, 1 place to the right. I need to adjust the exponent of the power. When you move to the right, you subtract the number of places that you move the decimal point. So the final answer for this problem is going to be 2.5, because now the point is going to be here, times 10 to the 8. So this is important. The final answer should be a number written in scientific notation. Okay, the last part of this example is part C. So we have now 5 times 10 to the negative 4 raised to the 3rd power. So we're going to get the cube of a number written in scientific notation. So the steps are, you're going to first distribute the exponents. So you're going to have the Mantissa to the 3rd power. And you're going to work now the power of 10. So you have negative 4 that multiplies 3, because now this is a power of a power. So in this case, we're going to get 5 to the 3rd power is just 5 times 5 times 5. times 10 to the negative 12. So 5 times 5 is going to be 125 times 10 to the negative 12. The decimal point goes here. So is this a mantissa? No, because it's a huge number. I need to move the point 1, 2 units. We need to move the decimal point 2 places to the left. And when you move to the left, you're gonna need to add, in this case, 2, because you're moving the decimal point 2 places. So you're gonna get 125. Now the point is in the right position, times 10 to the negative 10. So that's the final answer written in scientific notation. So the final assignment for this section and for this chapter, we're finishing now the chapter 8. So this is going to be just 2 problems. Problem 108, you're going to multiply 3 times 10 to the 4 by 3 times 10 squared. And then problem 118, you're going to divide 180 times 10 to the 8 over 2 times 10 to the 4. Here, this is a number that is not written in scientific notation, so this is just a division of powers of 10. So we're on these exercises, and this is the end of chapter 5.